All right, so we're going to start this new section introducing the idea of a derivative and how this concept can be thought of as a rate of change. And we're going to really start this off with a motivating example. All right, suppose we want to find the equation of the tangent line to a parabola at the parabola y equals x squared at the point 1, 1. So here's a picture of what that parabola looks like. And if I was to draw out the tangent line, it's going to look something like that. A tangent line touches the curve at one point and one point only. Well, unless it crosses over at a second time. But for around here, it touches at one point. Now, I'm going to first propose we solve this using algebra. So we want the two curves y equals x squared and this line, which I don't know what it is. I'm going to a line that goes through the point 1, 1 and has an unknown slope of m would be y equals m times x minus 1 plus 1. This is a way that you can put it into point slope form. And if we wanted to solve this thing, figure out what slope we need in order for this to happen, we can set the two expressions of x equal to each other and figure out what that would be, right? So if we set x squared equals m times x minus 1 plus 1, we have x, we can write this x squared, m times x minus m plus 1, right? Let's put everything onto the left-hand side, and we have x squared minus mx, and then we have plus m minus 1 equals 0. This is a quadratic in x, and the solutions, we would need m minus 1 to be minus m over 2, right? That's the only way that this would be a complete square, if you remember completing the square. And what that would mean, m minus 1 equals m squared over 4. What does this come out to be? M squared minus 4m plus 4 equals 0. This is just another quadratic. Now we can finally solve this. This actually factors as m minus 2 squared equals 0. In other words, m equals 2 is the only slope which would go up and give us only a single x value where this thing intersects. Otherwise, there would be two x values that would solve this equation. Okay, so that means the slope is 2, and we can take that slope and put it back into this equation. So we'd have y equals 2 times x minus 1 plus 1. Okay, but we can actually solve this. We can find the equation using algebra, but I want to propose we do this using this new tool that we have, limits, and see if this is going to do us a lot better. And let's look at how we would do that with limits, like what we want to think about. So using limits, you want to think about this, this point P and take some other point that's on the parabola, call it Q. And we want to think about whatever value we can take some, we know that P is at the point 1, 1, right? Q might be at, this is like approximately 2.4, comma, and then comes out to 2.4, comma 5.76. But the idea is you can connect P and Q together with a line, and that's called a secant line. And you can find out just from these 2 points, you can find out the slope of that secant line very easily, right? And you can actually take Q to be another point. I'll call that Q1 and maybe like call this Q2, for example. And you can find out the slope between P and Q2. The idea being, as you take points on the line that are getting closer and closer to P, the slope of the secant line is going to be more and more closely approximate the slope of a tangent line here at p, like the instantaneous rate of change, the slope at that point. And so we're going to try to write that in terms of a limit now. So the tangent line to the curve y equals f of x at some point p, which is where the x value is a and the y value is f of a, it'll be the line through p with the slope m equals the limit as x approaches a of f of x minus f of a divided by x minus a. So Q would be the point x comma f of x. And we let x get closer and closer to a, just as we did in the picture. And this is going to be the limit, this is going to be the slope as long as the limit exists. Now we can use h to be x minus a. And when we do that, we're going to get a bit of a different form of this. M is going to be the limit as h approaches 0. And in the up top, we're going to have f of x, f of a plus h minus f of a divided by h. It's a different form, but this is some that we've actually seen in earlier sections, and we've evaluated some of those limits. So we have a little bit of experience. Let's do an example. Let's find the equation of the tangent line to the hyperbola y equals 3 over x at 3, 1. So here's a picture of the hyperbola and the point, and this is approximately what that tangent line would look like, just a sense. So, all right, let's set this up as a limit. We would say m, the slope, is equal to the limit as h approaches 0 of f of 3 plus h minus f of 3 divided by h. This is the limit of this difference quotient. And let's put this into perspective. Let's evaluate the function at those 2 points. So this is the limit as h goes to 0 of, so f of 3 plus h is actually 3 over 3 plus h. And then minus f of 3 is 3 over 3. And then we just have this h here. And when we write it like that, we can start to figure this thing out. We notice that actually 3 over 3 can be just replaced by the number 1. So that's exactly what I want to do. I'll put just a 1 there. And actually, if I'm gonna sort this thing out, I actually want to clean up this numerator even more. And what I want to do is combine these 2 terms. The way to do that is to get a common denominator. The 3 plus h has to be on both of them. So I'm going to actually multiply 1 by 3 plus h over 3 plus h. In fact, I'll write it right here, 3 plus h over 3 plus h. And actually the 1 can just be discarded now. 3 plus h over 3 plus h. And let's actually take that numerator and add it. I'm going to do 2 things to help myself out. The limit as h goes to 0, I'm going to take the 1 over h and put it out front. That h in the denominator. And so we've got 3 minus 3 plus h all over 3 plus h. All right? This numerator is going 3 minus 3 plus h. That's, if we distribute the minus, we have 3 minus 3 minus h, right? So the 3 minus 3 cancels, we get a minus h. This is the limit as h goes to 0 of 1 over h times negative h over 3 plus h. And it's here where we can actually do a little bit of canceling. We see that we have an h on the numerator and denominator, and those can cancel with each other. And now when h goes to 0, what we get is negative 1 over 3, negative 1/3. And so this is my slope. And so the equation is going to be y equals negative 1/3 times x minus 3 plus 1. This is the general form. If you're going through the point 3, 1, 3, 1, this is the the equation of that line. And actually, to make sense a little bit, the slope being negative a third, that looks like a negative, well, certainly a negative slope. Negative a third, for every 1 unit across, it goes down by 3. Actually, it even looks like that. It appears that it's intersecting at 2 and roughly at 6. So that makes sense. Like it goes down by 1 for every 3 across. Go down by 1 for every 3 across. So if we have some function of t, where t is time, describing the position of some object moving around, we could find the velocity using similar techniques. And so the average velocity of the object between two times, time 1 at a and time 2 at a plus h, like so h units of time later, would be found using this difference quotient. So the position at time a plus h minus the position at a divided by how much time has passed. And so if you want to find the instantaneous, so the velocity at time a is the limit of this difference, of this average velocity as h approaches 0. Call that v of a, velocity at time a, for example. You could call it that. So for example, if a ball is dropped from 450 meters high, we're giving its position function, or it's the distance it's fallen, at 4.9 t squared at time t, where t is in seconds. So what's the velocity after 5 seconds? Well, let's figure that out. All right, so we'd have the limit as h approaches 0 of f of 5 plus h minus f of 5 over h. And what we have to do is we have to plug this stuff in to 4.9 t squared. So this is the limit as h goes to 0 of 4.9 times 5 plus h squared minus 4.9 times 5 squared, all divided by h. Now the 4.9 actually can be factored out, and then I'm going to expand the 5 plus h squared. So we're going to have 25 plus 10h plus h squared minus 25. So now what I've done is I've just squared both of those expressions, and when I do that, I can see that actually these 25s can cancel with each other. 25 minus 25, those are gone. So we have 4.9 times the limit as h goes to 0 of 10h plus h squared over h. H is a common term of all of these. In fact, I'm going to factor h out from the numerator, and when I do that, I'm going to remove that first h, and this is now going to be not h squared, but just h. And doing that, I can now cancel these h's, and so what I've got, the limit, what's this? The limit of 10 plus h as h goes to 0, this is going to be 4.9 times 10 plus 0 is just 10. So this is 49 meters per second. That's what the velocity is going to be at 5 seconds, at the 5-second mark. So let's ask, what's the velocity of the ball at the time it hits the ground? Well, we have to do one other thing first, and that's figure out what time it does hit the ground. When does 450 equal 4.9 t squared? That's when t squared is 450 divided by 4.9. That's when t equals, it's going to happen about 9.6 seconds. So now that we know we're talking about when t equals 9.6, we're looking at the limit as h goes to 0 of 4.9 times 9.6 plus h minus 9.6, 4.9 times 9.6 plus h squared. So it's the limit as h approaches 0 of 4.9 times 9.6 plus h squared minus 4.9 times 9.6 squared. Now I'm not going to expand out, I'm not going to multiply out 9.6, but I am going to do similar things that I did before. So I'm going to pull out the 4.9, and I'm going to get a very similar kind of thing happening, right? So I'm going to have 9.6 squared plus 2 times 9.6. All right, so 19.2, that's 9.6 times 2, 19.2. H plus h squared, that's what you get when you have 9.6 plus h squared. Okay, that's the first expression minus this 9.6 squared. And I'm again going to have these terms canceling. And then I'm going to write this like this. So we have the limit as h goes to 0 of, I'm going to take the h out like I did before. We have 19.2 plus h all over h. And we have, again, we can cancel the h's. And when h goes to 0, this is going to become 4.9 times 19.2. So it becomes 38.4 meters per second at the time of impact. That's the the final velocity of this dropped ball. So we're going to have define this derivative of the function f at a, or at the number a, when x equals a. We'll denote it with an f, a little apostrophe. It's actually, we call it prime. F prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h, if it exists. So let's take this as an example. Let's find f prime of a for this function x squared minus 8x plus 9. So we're going to have the limit as h approaches 0 of f of a plus h minus f of a all over h. So let's put the stuff into the function and just see what it'll all look like. We have the limit as h goes to 0, and then we've got a plus h squared minus 8 times a plus h plus 9 minus x squared minus 8x plus 9. I'm going to keep that all in parentheses because I want to make sure I distribute that minus sign properly. I don't want to make any mistakes there. I'm going to need to really expand this out and distribute and FOIL and do all of that stuff. So the first thing is the a plus h squared. It's going to be a squared plus 2ah plus h squared. Now we have the minus a plus h, so that's going to be minus 8a, and we'll have minus 8h, all right? Then we have plus 9, which is just plus 9. Now we're going to distribute this minus to all these terms. We're going to have minus, oops, what did I do before? I put x's instead of a's. I should have a's here. A here, a there. So we have minus a squared minus a minus, which is a plus 8a, and then we're going to have minus the 9. And at this point, a lot of stuff does cancel. A squared and minus a squared. Minus 8a and plus 8a, and we have plus 9 and minus 9. I didn't even draw the h underneath, or write the h, but it's there. Now let's write this numerator now that all of that stuff is cleared out. We have 2ah plus h squared minus 8h. That's what that all is, all divided by h. And we do have an h as a common factor everywhere, so if I factor out the h, we'll have h over h of what's left over. We've got 2a plus h minus 8. H over h is 1. And so the limit, when h goes to 0, we're just going to get a 2a minus 8. That is the derivative of this function at a. For any constant a that you would want, we've found it, the general form for this derivative. That's nice. So using the point-slope form of the line, of the tangent line equation, the line that's tangent to this curve y equals f of x, at this point that we've been using, where x is a and y, the coordinate, is f of a, can be written like this: y minus f of a equals f prime of a times x minus a. So here's a nice little general form of the tangent line equation, which can be handy. Let's take a look at an example using this. Okay, so say we wanted to find the line that's tangent to this curve, y equals x squared minus 8x plus 9, which we just looked at a second ago, at the point 3, comma, negative 6. So the point here that we want to observe is a is 3, f of a is the negative 6. We just need to evaluate like what's f prime of a for 3. So so from the previous example, we found f prime of a was 2a minus 8, sorry. So f prime at 3 is going to be 2 times 3 minus 8. That's 6 minus 8, or negative 2. So we have all the pieces to put into this equation. Y minus negative 6 equals negative 2 times x minus 3. Let's just clean it up a little bit. Y plus 6 equals negative 2 times x minus 3. If you, like me, you kind of like to have the y alone, so you can do that. Y equals negative 2 times x minus 3 minus 6. But any one of those is fine, but this is the one I'm going to go with. That's the equation of the tangent line that we're looking for here. So now let's think about a different way of defining this. If the value of x changes just a little bit from x1 to x2, we can define delta x as the change in x, the difference between x2 and x1. And then we can similarly define delta y as y2 minus y1. Or actually, let's be a little bit more explicit. It would be f of x2 minus f of x1, the function value, the difference in the function values. So the difference quotient, when expressed in this way, is going to be delta y over delta x. This is just f of x2 minus f of x1 over x2 minus x1, the average rate of change. So that's the average rate of change of the y value with respect to x over this interval x1 to x2. So then the instantaneous rate of change at the moment when x equals x1 is going to be the limit as delta x approaches 0 of delta y over delta x. It's just another way of writing the same thing we've done already a few times. Anyway, these are a couple ways in which we're tying this average rate of change or the instantaneous rate of change to this new concept, the derivative. Here we're evaluating, we can solve the derivative for certain types of functions at specific times, when x equals a, or x equals 5 or 7 or whatever. In the next section, we're going to generalize this and think about the derivative as a function in its own right. But that's another lecture. Bye.